Hi, welcome to xmTuition, where I help everyone with their physics homework. In this video, I'll be going through question 5 of the oscillations revision package. Let's get started. This question talks about a plate that's vibrating up and down, so it's oscillating up and down, and we're given this graph that shows the acceleration of the plate at different displacements. The question starts by making us explain how it may be deduced that the oscillations of the plate are simple harmonic. So what makes a motion simple harmonic? A motion is simple harmonic if its acceleration is equal to negative omega square x. Basically, to answer this question, we just have to explain how we can tell from this AX graph that A is equals to negative omega square x. So you're going to say, oh, because the AX graph is a straight line passing through the origin, that means A is directly proportional to x. But that's not the complete explanation yet, Because if there's no negative sign here, then the acceleration will be pointing in the wrong direction. But because the AX graph has a negative gradient, we know that the acceleration is going to be directed towards the equilibrium position, which means for this motion, we're going to have a restoring force. That's why it ends up oscillating. Okay, let's move on. In part B, we're asked to calculate the maximum speed of the plate. We all know that the maximum speed for a SHM is given by omega x naught. So our job now is just to figure out the value of omega. How do we do that? Because A is equals to negative omega square x. From the AX graph, the gradient of the AX graph is negative omega square. So just equate negative omega square to the gradient of the graph. Calculate the gradient of the graph. You can use any of these points here, but for accuracy, you should pick the larger value. So you're going to pick either this one or this one. Once you have the value for the omega, just plug into this equation here, you arrive at the correct answer. Part C, oh, now it gets interesting, We're going to sprinkle some sand onto the plate. So as the plate oscillates, the sand is going to oscillate together. And the question asks for the magnitude of the contact forces at different positions. Let's try to go through the dynamics of this motion. So we are most interested in the oscillation at these three positions: the equilibrium position, when it's at the bottommost position, and when it's at the highest most position. The equilibrium position is the easiest one because at the equilibrium position, we know the net force has to be 0, which means the downward weight of the sand is exactly balanced by the upward normal contact force that the plate exerts on the sand. So N is equals to mg. What about the other two positions? Now let me just quickly say that the weight of the sand is not going to change, no matter where you are during the oscillation. So mg is not going to change. So the only thing that's going to change will be the normal contact force. Okay, what happens at the bottom position? For SHM, the acceleration and your displacements are always in opposite directions. So when you're below the equilibrium position, the acceleration has got to be upward. And for the acceleration to be upward, net force has to be upward, which means the normal contact force must be larger than mg, so that you have a restoring force that tries to pull you back towards the equilibrium position. In fact, we can write it down as the equation here. The upward normal contact force minus the downward weight should be equals to my net force. And for SHM, the net force is the restoring force, which can be written as m omega square x naught. So you can see very clearly here that your normal contact force is not mg, it's larger than mg. By this amount here. It must be larger by this amount so that you have the restoring force to produce the simple harmonic motion. Okay, what about when you're at the topmost position? So when you're above the equilibrium position, you know the acceleration is downward, so you know the net force is downward. So you know the normal contact force must be smaller than your weight. We can write it as an equation here. The downward weight minus the upward normal contact force is equals to my net force, which is m omega square x naught for a SHM. So you can see very clearly here, the normal contact force is not mg. It's smaller than mg by this amount here. It must be smaller than mg by this amount so that you have a restoring force to produce the simple harmonic motion. Okay, if you follow all that, then these calculations should be very easy. So at the equilibrium position, the normal contact force is exactly equals to your weight, and so this is the normal contact force at the equilibrium position. When you're at the lowest most position, the normal contact force has to be larger than mg. We know m times a is actually the restoring force, is the m omega square x naught here. For this question, it's easier to just read from the graph the acceleration at the lowest position. So at the lowest position here, you can read from the graph the acceleration is 7 meters per second square. So I can simply substitute A to be 7.0 meters per second square. So sure enough, the normal contact force is stronger at the bottom compared to when it's at the equilibrium position. Let's move on to part D1. So we are told that the amplitude of the oscillation of the plate is maintained, but the frequency is gradually increased. We're asked to determine the frequency at which the maximum acceleration is equal to the magnitude of the acceleration of free fall. Basically, the question is asking when is your A equals to g, 9.81 meter per second square. For SHM, s goes to negative omega square x, so you know the maximum acceleration happens at the extreme positions. That's why the maximum acceleration can be written as omega square x naught. And we're going to equate this to 9.81 meter per second square, as the question says, yeah? So do all the calculations, the frequency turns out to be 6.23 Hz. Now, let's move on to the last part of the question. Suggest, with a reason, what happens to the sand on the plate in which when the frequency of the oscillations exceeds the value we calculated earlier. I think exam smart students will guess that this has something to do with the sand losing contact with the plate. And sure enough, yep, if you exceed that frequency, the sand is going to lose contact with the plate. Why is that so? Because the acceleration or deceleration of the plate will be too fast for the sand to keep up with. So for exam smart students, even if they don't fully understand the whole thing, they may be able to smoke out by writing this down. But of course, I'm going to make sure that you understand the full thing. So let me ask you a question. When do you think the sand will lose contact with the plate? That's the same as asking when the normal contact force becomes zero. The math shows it very clearly, yeah? The sand is never going to lose contact when you are anywhere below the equilibrium position. The normal contact force is always larger than mg. If anything, if you increase the frequency, the normal contact force just becomes stronger, which means the sand and the plate press into each other even more strongly. It's only when the motion is above the equilibrium position when the normal contact force can drop to zero. See here? The normal contact force is less than weight. In fact, if you gradually increase the frequency, there will come a frequency high enough such that the normal contact force becomes zero. And the normal contact force becoming zero means that the sand lose contact with the plate. But still, you're going to ask, why does that happen? So let's visualize the motion step by step, yeah? Let's start with the motion when it's at the bottom. So both the sand and the plate are at rest, and the plate is trying to accelerate upward. What is the sand trying to do? It's trying to accelerate downward actually, because the gravity is pulling it down, right? So if the plate allows the sand to have its way, it actually means that the sand will puncture a hole in the plate, right? So the plate has no choice but to push the sand hard upward. That's why during this part of the motion, the sand and the plates will be pressed hard against each other. Okay, now let's talk about the motion between here and here. At this point of the motion, both the plate and the sand are moving upward at their maximum speed. And the plate is now trying to slow down. What is the sand trying to do? Because of gravity, it's also trying to slow down. But if it's slowing down slower than the plate, then the plate will still be pushing the sand, which means the sand and the plate will still be pressed against each other. But if the plate is slowing down faster than the sand is free falling, then it just means that the sand will race ahead of the plate, which means it loses contact with the plate. Do you see what's happening? Now, what about on the way down? Let's start from here. Let's say the sand and the plates are both at rest, and so the plate is trying to accelerate towards the equilibrium position. The sand is also trying to free fall towards the equilibrium position. So if the plate is accelerating downwards more slowly than the sand, then the plate and the sand will still be pressed against each other. But if the plate is accelerating faster than 9.81 meter per second square, just means that the sand doesn't speed up as fast as the plate. What does that mean? It means the sand will fall behind the plate, and that's why they lose contact. What about this part of the motion? So if both the sand and the plate starts the motion from here, then they are already at a maximum speed. And during this part of the motion, the plate is trying to slow down. But the sand is trying to speed up, because of gravity, the sand is actually trying to speed up downwards. So again, if the plate lets the sand have its way, it means that the sand will puncture a hole through the plate. So the plate has no choice but to push the sand upward. It also explains why the plate and the sand will be pressed against each other during this part of the motion, because the plate is trying to slow down but the sand is trying to speed up. So naturally, they'll be pressed against each other. So basically, the sand can lose contact with the plate only during this part of the motion. It may lose contact on the way up simply because the plate slows down faster than the sand. It can also lose contact on the way down simply because the plate speeds up faster than the sand. Okay, that's all I want to say for this question. See you in the next one. Ta-ta!